Okay guys, so we're going to start talking about molecular geometry, and in order for us to do this we're going to have a little recap on Lewis structures and how they function. Now, let's get a recap of Lewis structures. For example, if you have a molecule such as methane, CH4, to find the appropriate Lewis structure, what we're going to have to do is we're going to have to calculate the total valence electrons that are going to be displayed in our molecule. You start off by finding out how many different elements do I have present in this molecule. I have two, one carbon and hydrogen. Those are two different elements. We're going to start off by jotting down the first element. The first element is carbon. How many carbons do we have present? We only have one. So what we're going to do is we're going to say one atom of carbon, and we're going to multiply this by the valence of carbon. Now, if you recall, on the P block, groups 13 through 18, we can do the group minus 10 rule to find out what's the valence on those atoms. Carbon is under group 14, so 14 minus 10 gives us 4 valence electrons. Now, there's 4 valence electrons for every one atom of carbon. And we're going to add this to the second atom. The second atom we have is hydrogen. Now, how many atoms of hydrogen do I have present in this molecule? We have 4 atoms of hydrogen. So what we're going to do is we're going to put 4 atoms of hydrogen, and we're going to multiply this by the valence. Now, group 1 will always have a valence of 1. Group 2 will always have a valence of 2. So hydrogen is in group 1. So we have 1 valence electron for every one atom of hydrogen. Now if we do the basic mathematics, we have 1 times 4 divided by 1, which is 4, plus 4 times 1 divided by 1, which is 4. If we add them up, we should get a total of 8 valence electrons. So when I draw this structure, I'm wanting to see 8 valence electrons. Okay? So let's go ahead and work this problem out. Now, remember that every atom wants to have a complete octet. There is a couple of exceptions. Hydrogen and helium do not have an octet. The reason being is because they only have the s orbital. And the s orbital can only have 2 electrons. So we're going to go ahead and write down which atom can make the most bonds. Okay? Which atom can make the most bonds? Now, since hydrogen only has a valence of 1, and its maximum amount of valence electrons that it can obtain is 2, each hydrogen can only make 1 bond. So that's not going to be the one that can make the most bonds. However, carbon has 4 valence electrons. So that means it can make 4 bonds so it can reach its octet. So that's exactly what I'm going to do. I'm going to go ahead and bond carbon 4 times to hydrogen. Now, if we look at the structure, okay, we're going to have to count our electrons. Now, we can do this simply by checking out the bonds that are present here. Now, remember that each bond counts as 2 valence electrons. So we have 2, 4, 6, and 8. So we match the 8 from earlier. We need to make sure that every atom is happy in this molecule. So if we look at this, hydrogen has 2 around it. So around this hydrogen, there's 2 valence electrons. Around this hydrogen, there's 2 valence electrons. Around this hydrogen, there's 2 valence electrons. And around this hydrogen, there's 2 valence electrons. So the hydrogens are happy. We need to make sure that carbon is happy. Well, carbon has got 2, 4, 6, and 8. So carbon reaches its octet as well. Therefore, carbon is happy. Therefore, the correct structure was given for this molecule. Now, it is not in there, however. We need to find out how the molecule looks in 3 dimensions. So we're going to introduce something called valence shell electron pair repulsion, also known as the Vsepr theory. Now, in order for us to do this, we're going to have to take out some of the notes that we previously had in our class. In order for us to do that, well, let's go ahead and load up those notes. This is what our notes look like. Now, when we had the structure of carbon, we had C and 4 bonded hydrogens. Okay. This is what methane looked like. I'm sorry, not hydrogen. This is what methane looked like. Now, what we're going to do here is we're going to look at a couple of groups that are noted here on our notes. We're going to look at the number of lone pairs of electrons on the central atom, the number of bonding pairs here on the central atom. Once we do that, it will tell us our electron pair geometry, which is one thing that we want to know, the molecular geometry, which is going to be our shape, and it's also going to tell us the bond angles at which these hydrogens and carbons are located. So, the very first step, go ahead and count how many lone pairs of electrons do I have around the center carbon. Now, if you notice, for the molecule methane, we have 0 lone pairs on the central atom. We do not have dots around the carbon. So there's a couple of things that I can look here. Well, I can scratch off anything that has 1 under the lone pairs. Okay, we're not going to use that for this problem, so we can go ahead and scratch that off. Okay, so we're left with the ones that are not scratched off. Second thing, we're going to look at number of bonding groups around the central atom. Now note that around carbon we have 1 bonding area, 2 bonding areas, 3 bonding areas, and 4 bonding areas. So that can also help us eliminate some more in our chart that are not needing to be here. Here we only have 2 number of bonding, so we can delete that. 3 number of bonding, so we can delete that. 5 number of bonding, I can delete that. And 0 bonding, so I can delete that. This leaves us with only 1 possible option. Now we're going to have to do this process of elimination for these molecules a couple of times. This gives us this shape. Now, our number of lone pair of electrons on the central atom is going to be 0 because we didn't have any here. The number of bonding groups, we're going to have 1, 2, 1, 2, 3, and 4. So we have 4. So our electron pair geometry comes out to be tetrahedral. Our molecular geometry happens to be tetrahedral as well. And our bond angle, which is one of the most important things, is going to be 109.5. Okay, this is how molecular geometries work. Now, we're always going to use this chart. And it's always going to be very, very useful to us. Okay, so another thing that we can do, let's say we have another molecule. For example, let's say we had H2O. Okay, so suppose we had H2O. So once again, we do the Lewis structure. So we have water. We do the Lewis structure. We start with identifying how many elements, 2 elements. How many atoms of the first element? Well, we have 2 atoms of hydrogen multiplied by the valence. Now the valence of hydrogen is in group 1, so it's got 1 valence electron for every 1 atom of hydrogen. Plus, how many atoms of the second element do we have? Well, we have 1 atom of oxygen multiplied by the valence of oxygen, which is 4 valence electrons for every 1 atom of oxygen. Now, oops, I apologize, I made a mistake. We're going to go ahead and delete that. Oxygen is actually in group 16, so we have 6 valence electrons. So when we do the math, we have 2 times 1 divided by 1, which is 2, plus 1 times 6 divided by 1, so 1 times 6 divided by 1, which is 6, and 2 plus 6 gives me 8. So when I draw this molecule, I have to be showing 8 valence electrons. This is the key number. Okay, the way we're going to go ahead and do that is we'll draw the one that can make the most bonds in the center. Now note that hydrogen can only make one bond, so it can reach its 2. Remember that hydrogen does not follow the octet rule. However, oxygen has 6 valence electrons, so it needs 2 more electrons to get to its octet. Therefore, oxygen is going to go ahead and follow the octet rule. So it's going to be able to make 2 bonds, which is the most important. That means oxygen will be our center atom. So what we're going to do is we're going to go ahead and draw oxygen, and we're going to bond it to the 2 hydrogens that are present. Now, if we do that, we're only displaying 2 and 4 valence electrons. Now, we need to display 8. Remember that 8 is our key. But oxygen still hasn't reached its full octet. So what we're going to do here is we're going to go ahead and add lone pairs of electrons around the oxygen. Now, if we do the math, we have 2, 4, and then the bonds 6 and 8 around oxygen. So oxygen has reached its octet. We have 2 around hydrogen and 2 around hydrogen. Therefore, the correct structure for the water molecule looks like what we drew. Okay, but it doesn't end here. Once again, we have to identify the molecular geometry. Now, we're going to go back to the structure that we had prior to this. Okay, and if we look at this, we have the water molecule, and it looks something like this. Yeah. Okay. Now, if we look at this, we notice that we have 1, 2 lone pairs around the center atom. Okay, and then we have 1 and 2 bonded pairs around the center atom. So we're going to look at lone pairs. We should have 2, so we can eliminate anything that does not have 2 right off the back. You can delete that, and that. Now, we have 2 bonded pairs as well. So look at this one. We have 2, we have 2. So therefore, that is what it's going to look like. Now, if we look at our electron pair geometry, we have a shape of tetrahedral. But our molecular geometry, what our figure is going to look like, it's going to look bent. Now, bent is going to be the structure that I drew for you. It's going to look something like that. Okay. So what are the bond angles? Well, the bond angles here are between 109.5. Okay, and this is what you're going to have to do for electron pair geometry. Now, tomorrow you will have a worksheet on this. The worksheet will have a couple of example problems, and we will work them out in class. If you have any questions, feel free to ask me. I have no problem answering any questions that you may have. But this is it. Thank you.